Hello and welcome back to Wind Chemistry. Today we're going to study the various gas laws and how pressure, volume, temperature, and the number of particles affect the behavior of gases. So let's jump right into it. We're going to study Boyle's, Charles, Gay-Lussac's, and finally the combined gas law to see how all this fits together. Before we get into these gas laws, you do have to understand that we use a unit called Kelvin to measure temperatures. So if you want to go from Celsius to Kelvin, you would have to add 273 to that. So 300 Kelvin is really 27 degrees Celsius, which is slightly warmer than room temperature. Temperature is the measure of average kinetic energy, and the equation is 1/2 mass times velocity squared. And you can see this for yourself. The average temperature right now is 300 Kelvin, but it's a mixture of the blue and the red gas molecules, and they're all different sizes. So because the smaller gas molecules, the red ones, have less mass, they have to move faster so that they can have the same kinetic energy as the bigger gas molecules. Boyle's law describes the inverse relationship between pressure and volume. So that means temperature is being held constant. You can see how the T's are canceled out in my equation there. So we're left with Boyle's law. And Boyle's law, I'm going to click temperature right there to keep it constant. So that means the only things I can change now are the pressures and the volumes of this container. So we have the gas inside the container, and to many of you this is intuitive. So if I drag this handle over towards the left to increase the volume of this container, I expect the pressure to go down, and it does. So the pressure went down. Now if I squeeze on this box, if I decrease the volume, I expect the pressure to go up, and it does right there. And so the pressure nearly doubles. Charles' law describes the direct relationship between volume and temperature. So we could see in the equation for the combined gas law how pressure is crossed out. They're canceled out because pressure is being held constant. And in the simulator here, we're going to go ahead and click the bubble for pressure because we want that to be held constant. So check that bubble. And now we can do stuff like change the heat. But look at the pressure and look at the temperature and the volume. Okay, so we're going to study all three in tandem here. If I heat this container up, you can see the temperature increases and the volume also increases. So they both go up, but the pressure remains constant at 10.9 atmospheres. If I cool this container, the temperature goes down and the volume goes down. So they both decrease. Again, it's a direct relationship between these two variables as pressure and the number of particles is being held constant. I can also check this bubble here. So that will take the hot and the cold away, but I can change the volume. So if I increase the volume, the temperature should go up on its own. And if I decrease the volume, some ice will pop out. You're going to see it here. I'm not adding in the ice or anything, it just happens on its own. But the pressure remains constant at 10.9 atmospheres. Gay-Lussac's law describes the direct relationship between pressure and temperature. So if nothing is being held constant, that means I can change the volume of the box. That's why that handle appears. But as soon as I click that, the handle disappears on the left-hand side of the container. Now, if I heat this container up, I expect the temperature to go up and the pressure should go up as well because that's what the gas law describes. So if I heat this thing up, you can see the temperature is climbing and the pressure also increases. So pressure goes up, temperature goes up. And again, just to show you, if I click nothing, the handle reappears. That means I can change the volume, but we're keeping the volume the same, which means the size of this container should always remain the same. Now if I cool down the container, if I ice this container, the temperature goes down. The size of the box remains the same, but the pressure also goes down accordingly because that's what Gay-Lussac's law describes. Temperature goes down, pressure goes down. If I heat it up, I expect the molecules to also move faster because the kinetic energy is also going up, which means the temperature is increasing. Temperature goes up. The barometer also goes up. You can see the needle is climbing, so the pressure also increases. So they both move in the same direction. So in short summary, before we start doing some of these gas law equations, all three gas laws can be derived from the combined gas law. You just have to know that the number of particles is being held constant. Boyle's law is the only one with an inverse relationship. And finally, before you start plugging in for temperature, make sure it's always in Kelvin, and to do so, you always add 273 to the Celsius temperature. Let's do a Boyle's law problem. This would be practice problem number 1 on page 422, but in your notes it's number 6. And let's read through it. It says the volume of a gas at 99 kilopascals is 300 milliliters. So I'm just going to call 99 kilopascals P1. That's my initial pressure. My V1, my initial volume, will be 300 milliliters. If the pressure is increased to 188 kilopascals, what will be the new volume? So they tell us what P2 is, and V2, I'm going to write a question mark for that because that's what we're going to solve for. So you just need some basic algebra skills to solve this problem. And I'm going to start with something called the combined gas law. And I noticed that in the problem, T is not given at all. So that means temperature is being held constant. I can cross out T's on both sides of the equation, and I'm left with what Boyle's law describes, and that is the inverse relationship between pressure and volume. I'm going to circle V2, and then how do you isolate for V2? We're going to divide both sides by P2. So that's the equation I'm going to use. V2 equals P1 V1 over P2. And now we just need to plug in. It's just plug and chug. V2 is equal to, we're going to plug in P1 here, 99. Multiply that by the initial volume, 300 milliliters. And divide by the new pressure, 188 kilopascals. Units are important. You're going to see how the units cancel out. Kilopascals would go away, and you're left with milliliters, which is a unit of volume. So that means we're doing it correct so far. And now we just need a calculator at this point. Just go 99 times 300 over 188. And let's see what we get. V2 is 158 milliliters. And it's just as we expected. If the pressure goes up, the volume should go down just slightly. So the volume went from 300 down to 158. And that describes Boyle's law, which is the inverse relationship between pressure and volume. Pressure goes up. So pressure went from 99 to 188. And the volume will drop. Okay, so think of it as a squeezing effect. Okay, pressure goes up. Pressure is like squeezing on this container, this gas container, and it causes the volume to go down. This one's another Boyle's law problem. Problem number 5 on page 422 of your textbook. It's numbered differently than notes. It's number 8 in your notes. But this one, let's read through it. It says a sample of neon gas occupies 0.22 liters at 0.86 atmospheres. So that means your initial pressure and volume are provided. So P1 is given as 0.86 atmospheres, and V1 is 0.22 liters. And now it's asking what will be its new volume at 29.2 kilopascals. So P2 is given. V2 is what's being asked in the problem. So let's give that a question mark. And now it says you need to convert one of the pressures, and it doesn't matter which one, but they both have to be in the same units, either atmospheres or kilopascals, to continue on with the problem. Otherwise the units don't cancel out. So let's just pick one. Okay, I'm going to pick P2, and we're going to change kilopascals into atmospheres. I think it's easier working with numbers in atmospheres, but really it's all a matter of preference, and we know how to do conversions. Okay, time sign, draw a line, make sure the units cancel out top and bottom. 1 atmosphere is equal to 101.3 kilopascals. Okay, so take 29.2, divide by 101.3, and let's see what our new atmospheric pressure might be. So 0.288 atmospheres. So we have P2 as a different unit now. Let's go ahead and erase that so it doesn't confuse you. P2 is 0.288 atmospheres, and now we can continue with the problem. We can solve for V2 just like how we did in the previous problem that I just showed. I'm going to go ahead and erase this, get that out the way. And now P1 V1 equals P2 times V2, which is Boyle's law. I'm going to circle V2 because that's what we want to solve for. And V2 is equal to P1 V1 over P2. At this point, it's plug and chug. Make sure everything is in order. Plug in your P1. Plug in your V1, 0.22 liters, easy. And then divide by P2. And our P2 is going to be 0.288 atmospheres. So now it's apparent why we had to do that conversion at the start of the problem. So now atmospheres will cancel out, and liters is left behind. Liters is a unit of volume, so that tells us we're doing it correctly. Okay, and now solve for this expression. This would turn out to be 0.657 liters, which makes sense because, again, Boyle's law says pressure and volume are inversely related. So if the pressure goes down, it went from 0.86 to 0.288, and the volume goes up, that should confirm Boyle's law because, again, it's an inverse relationship for Boyle's law. Pressure goes down, volume should go up in this case. Alright, here we go. We're going to do a Charles law problem. And let's read through it. A gas at 89 degrees Celsius occupies a volume of 0.67 liters. So right away, I know that I'm given T1 and V1. At what Celsius temperature will the volume increase to 1.12 liters? And now let's write down our variables nice and neat so that we stay organized for the entire problem. V1 is equal to 0.67 liters. T1 is 89 degrees Celsius, but there's a quick change we have to make. We have to convert Celsius to Kelvin for all gas law problems involving temperature, and the way that we do that is we add 273. So from now on, we're going to plug in 362 Kelvin for T1. Our V2 is given as 1.12 liters, and our T2 is a question mark, so that's what we're going to set out to solve for. We're going to solve for T2. So we need to find what the formula is, first of all. And I'm going to start with the combined gas law. Okay, and now I go back to the problem, and I ask myself, well, what variable is not provided? And it looks like pressure is not stated at all in the problem, so that means pressure can be assumed to be constant, which means you can cross it out, and then the variables that you're left with in that order will be Charles's law. So Charles's law is V1 over T1 equals V2 over T2. Now we're going to solve for T2. So we're going to cross multiply and then do a little bit of algebra to find out what T2 is. So let's go ahead and cross multiply these variables. So T2 V1 is equal to T1 V2. So that's what I did right there. I did cross multiplication. And now we want to isolate for T2. And the way that we do this is we're going to divide both sides by V1. So now that looks good. I'm going to go ahead and box that. And we're going to write it nice and neat up here. T2 is equal to T1 V2 over V1. go ahead and erase all this right here. Get that out the way because we're running out of room. I wrote down the formula so we wouldn't forget, and now we just plug in. Plug and chug. 362 Kelvin times 1.12 liters over, and our V1 was 0.67 liters. You can see the L's will cancel out, liters will go away, that's great. And we're left with Kelvin, which is a unit of temperature. So now you just need a calculator at this point. Take 362 times 1.12 and divide by 0.67. And we're going to get 605 Kelvin, but we're not quite done with the problem just yet. We want to go ahead and subtract 273 because the problem wants it back in Celsius. So our answer is 332 degrees Celsius, which makes sense because V1 is 0.67 and it increased to 1.12 liters. So Charles's law says temperature should also go up from 89 to 332 Celsius. We're going to do a problem involving Gay-Lussac's law. So in this problem, it says a gas in a sealed container has a pressure of 125 kilopascals. That's our P1. Our T1 is 30 degrees Celsius. If the pressure in the container is increased to 201 kilopascals, that's our P2, what is the new temperature? So solve for T2. Let's write down our variables nice and neat. P1 is 125 kPa, kilopascals. T1 is 30 degrees Celsius, and immediately we're going to add 273 to that to change it into Kelvin so we don't forget. P2 and T2, let's figure this out. So T2 is what we're going to solve for. Our P2 is 201 kilopascals. So we expect the temperature to go up because the pressure has gone up. Let's start by writing down the combined gas law, as always. Okay, eventually you can just skip straight to the formula, but since this is the first problem that we're doing for this particular gas law, I want to show you how volume is being held constant, so that means it's going to cancel out. So our new gas law for Gay-Lussac's is going to be P1 over T1 equals P2 over T2. And now we're going to solve for T2 by cross multiplying. So we're going to go ahead and cross multiply these variables here. T2 P1 equals P2 T1. T2 is equal to P2 T1 over P1. Okay, make sure it's all in the right order. So that's how we got our T2 to isolate. So that's our equation that we want to use to solve for the new temperature. And at this point, we're going to go ahead and plug in. Just plug and chug, make sure everything is in the correct order. So Kelvin will go there for T1. And divide that by 125 kilopascals. kPa will get canceled out. That's great. We're left with Kelvin. It's a unit of temperature. Perfect. So figure out this expression on the calculator. Okay, 201 times 303 divided by 125. And we're going to get 487 Kelvin. Okay, so this one didn't specify Celsius, so I guess you don't have to change it. You can just leave it as 487 Kelvin. And it's apparent that, yes, the temperature has gone up. It's gone from 303 to 487 Kelvin, which is what Gay-Lussac's law describes. It's the direct proportional relationship between pressure and temperature. One of them goes up. The other one should also go up as well. And if you were to change it, just subtract 273, and you get 214 degrees Celsius for this problem. We're going to do a combined gas law problem. We're going to read through it. And it says a helium-filled balloon at sea level has a volume of 2.1 liters 0.998 atmospheres and 36 degrees Celsius. So right away, we're going to organize these variables before we continue reading. Okay, our P1, our initial pressure is 0.998 atmospheres. Our V1 is 2.1 liters. And our T1 is 309 Kelvin. Remember, you have to change Celsius into Kelvin by adding 273. So that's taken care of. Now on the right hand side over here, we're going to figure out our final pressures, volume, and temperatures. So if it's released and it rises to an elevation at which the pressure is 0.9 atmospheres and the temperature is 28 degrees Celsius, what's the new volume of this balloon? So because it's asking what's the new volume, I know right away we're supposed to solve for V2. So for our P2, it's going to be 0.9 atmospheres, and our T2 is 28 plus 273, because we want to get that into Kelvin. So it's going to be 301 Kelvin. That's what we're going to plug in once we get to the equation. So to give you an illustration here, here's our balloon at sea level. You have your stick figure man, and you release this balloon. The problem is asking for what is going to be the new volume. So will the balloon expand or will it shrink? Will it compress? Okay, and that's what we're going to try to solve for. I'm going to write out the equation. This is the combined gas law. So in this case, like, none of the variables are being held constant. I'm going to circle V2 because that's what we're going to solve for. So it's a bit of algebra. Okay, and we're going to multiply this by T2 over P2 to get them to switch, to isolate for V2. Okay, it's simple algebra. So at this point, we're going to start plugging in. So for P1, 0.998 atmospheres. For V1, 2.1 liters. And our T1 is 309 Kelvin. And we're going to multiply this by T2 over P2. So T2 is 301. And our final pressure is 0.9 atmospheres. Cancel out the atmospheres. Cancel out the Kelvin. And it looks like we're left with liters. That's great. That's a unit of volume. So you can see there in purple, I highlighted it. We're doing good so far. All the units are canceling out the way that they're supposed to. And at this point, you just need a calculator. Get this expression in. 0.998 times 2.1 times 301, hit enter, and then divide by the expression on the bottom. We're going to get 2.3 liters. So that's our final volume, that's our V2, and it appears like the balloon has expanded, which makes sense because if you release a balloon and it goes into the atmosphere, there's less air pressure, so the balloon is able to expand. Temperature also gets slightly colder. Okay, so it appears that the balloon will expand. It gets slightly larger. It goes from 2.1 liters to 2.3 liters.